Welcome to Geek Lectures. Hi friends, I'm Helena. In today's topic, we will be dealing with deadlocks and how it can be handled. Let's begin the class.
Deadlock. A deadlock is a state in the system where each process in the deadlock is waiting for an event that the other process in the set can cause. Consider a real-time example where two trains are approaching each other on the same track and at the same time. When both of the trains are approaching each other, they cannot move after one another. This situation is called deadlock. Similar is the case in the case of operating systems. In operating systems, deadlock can be easily explained with the help of a graph called resource allocation graph. Here consider two resources, resource 1 and resource 2, and two processes, process 1 and process 2. The resource 1 is assigned to process 1 and is waiting for resource 2. Similarly, process 2 is assigned with resource 2 and is waiting for resource 1. Here both of the processes will not begin their execution unless their resource requirements are satisfied. This condition is called deadlock. There are four necessary conditions that must be held simultaneously for deadlock to occur. They are mutual exclusion, hold and wait, no preemption, and circular wait. First, mutual exclusion. It means each resource in the system is either available or currently assigned to exactly one process. That means a single process should only utilize a resource at a time. Next, hold and wait. Processes are currently holding some resources and are waiting for some other resources that must be acquired, that should be acquired for the process to begin its execution. This condition is called hold and wait. Next, no preemption. Essentially, it should not be the case that resources which an operating system previously granted for a particular process is forcibly taken away from that process. That is, the OS or another entity in the system cannot forcibly remove a resource which has been allocated to a particular process. Instead, processes should explicitly release the resource by themselves. That is, whenever the process wants it, it should release the resource by itself. Circular wait. There must be a circular chain of two or more processes, each of which is waiting for a resource held by the next member of the chain. Next, the methods for handling deadlock. There are three methods for handling deadlock. They are deadlock prevention or avoidance, deadlock detection and recovery, and ostrich approach or ignoring the problem of deadlock altogether. First one is deadlock prevention. For preventing deadlock, we can prevent any of the four necessary conditions for a deadlock to occur. So first, eliminate mutual exclusion. It is always not possible to eliminate the condition of mutual exclusion because some of the resources are non-shareable. Example of non-shareable resources are tape drive and printer. So in such cases, we cannot eliminate mutual exclusion. Next, eliminate hold and wait. Allocate all required resources to the process before start of its execution. This way, hold and wait condition is eliminated, but it will lead to low device utilization. For example, if a process requires printer at a later time and we have allocated printer before the start of its execution, printer will remain blocked till it has completed its execution. It may not be feasible to know resource requirements. Also, it may not lead to an optimal usage. Next, here in the graph, we can see that resource 1 is assigned to process 1. Process 1 is waiting for resource 2. This is the condition called hold and wait. Next, eliminate no preemption. Preempt resources from process when resources are required by other high priority processes. In this way, we can eliminate this condition too. Next, eliminate circular wait. Each resource will be assigned with a numerical number. Process can request for the resources only in the increasing order of numbering. For example, if P1 process is allocated R5 resources, now next time if P1 asks for R4, R4 is less than R5, therefore such request will not be granted. Only a request for resources more than R5 will be granted. Next, deadlock avoidance. By avoidance, we mean that the system will never go into a state which could potentially create a deadlock situation. System decides in advance if allocating a resource to a process will lead to deadlock. Deadlock avoidance can be done with the help of Banker's algorithm. Banker's algorithm. This is resource allocation and deadlock avoidance algorithm. It tests all the requests made by the processes for resources. It checks for a safe state. Then, if after granting the request, the system remains in the same state, safe state, then it allows the request. And if there is no safe state, it doesn't allow the request made by the process. Then what do you mean by a safe state? A state is said to be safe if there is some scheduling order in which every process can run to completion, even if all of them suddenly request their maximum number of resources immediately. An unsafe state can lead to a deadlock state. Next, the input for the Banker's algorithm are the maximum need of resources by each process, currently allocated resources by each process, and maximum free available resources in the system. The request made by a process will be granted only under the below condition. If the request made by the process is less than or equal to the maximum need of that process, or the request made by the process is less than or equal to the freely available resource in the system. If only these conditions are satisfied, then only the request will be granted. For example, here consider the total resources in the system as for process A has 6 resources, B has 5 resources, process C has 7 resources and D has 6 resources, and the available system resources are A has 3 resources and B and C have 1 resource each and D have 2 resources. And the processes currently allocated with the resources are process 1 is associated with 6 resources of A and 5 resources of B and 7 resources of C and 6 resources of D. And the maximum resources for the processes are similarly shown as the needed amount of resources can be found out by the maximum resources minus the currently allocated resources. Thus the needed resources are process 1 has 2 resources of A and 1 resource of B and 1 resource of D, and it does not have any resource of C. Similarly for the processes P2 and P3. Next, deadlock detection. First case, if the resource has single instance. In this case, for deadlock detection, we can run an algorithm to check for cycle in the resource allocation graph. Presence of a cycle in the graph is a sufficient condition for a deadlock. In the diagram, resource 1 and resource 2 have single instances and there is a cycle R1, P1, R2, P2. So, deadlock is confirmed. Next case is if there are multiple instances of the resources. Detection of a cycle is necessary but not sufficient condition for deadlock detection. In this case, system may or may not be in a deadlock state. Next is deadlock recovery. Traditional operating systems such as Windows doesn't deal with any deadlock recovery mechanisms, as it is time and space consuming process. Real-time operating systems use deadlock recovery. And the recovery methods are, generally there are 3 methods: killing the process, resource preemption and rollback. First, killing the process.
Killing the process. Killing all the processes involved in deadlock, or killing each process one by one. After killing each process, then check for the deadlock again. Keep repeating the process till the system recovers from deadlock. Next is resource preemption. Resources are preempted from the processes involved in deadlock. Resources are then allocated to other processes so that there is a possibility of recovering the system from deadlock. In this case, the system may go into starvation. It means infinite waiting of resources. Rollback. Certain checkpoint states are created and then roll back when a deadlock is detected. When a deadlock is detected, then roll back to the last checkpoint and the process continues its execution from there on. Thus, the system may recover from deadlock. Next, the issues related with deadlock will be dealt with in the next video.
Thank you all for watching my video. I hope you understood the concepts. If you like my video, please do like it and please subscribe my channel to get more videos. And also, don't forget to press the bell icon to get notified when I upload new videos. Please give me your valuable feedback in the comment section. Thank you and have a great day.